Give them 1 minute, I don't know. It's 0.9. Oh, it's 30 minutes. But I still really do think it's
Okay, yeah, so I kind of need this to be done. So I can use this. Now I think you problem.
Okay, I think it's time to start. Welcome everybody to this docent lecture by Raphael van Laer. I should start by introducing Raphael to those of you who don't know him, but I think I know you do. Raphael got his PhD in 2016 from the University of Ghent, the IMEC Institute. And then he spent 5 years at Stanford University, right, as a postdoc. And then he joined Chalmers in 2021 as an assistant professor. That is his current position. Raphael has managed to secure a number of very impressive and prestigious grants. For example, SSF Young Research Leader Grant. I was only a starting grad. He also has a very nice publication record with an H index of 19 and 1900 stations, which is probably unusual. So we're very proud of you, Raphael, and it's my pleasure to introduce Raphael to give his docent lecture. Docent is the first step on the academic career. After this, Raphael can be main supervisor. So without further ado, please go ahead, Raphael, and let's take the questions afterwards. There might also be questions on Zoom. You should be aware that this will be recorded on Zoom. So any stupid questions that you have will be recorded for there. Okay, thank you very much.
Okay, so good morning, everyone. And thanks for the introduction, Magnus. So welcome to my talk. The goal for the talk, for me at least, is mainly pedagogical. So I'd like to give you especially the background and the understanding at an intuitive level for what we are doing now, and also for where we are going in the future, hopefully. So focusing especially on the intuition that's at the basis of what we do, and a little bit less on my pre-Chalmers work also. So especially what's related to what we're doing here at Chalmers. So our group is the quantum photonics lab, or that's what we'll call ourselves at least for now. And the photonics there stands for both optical and microwave photons. So we work with these microwave and optical frequencies, and we try to have them interact with each other and also with themselves. And then also we want to have them interact with high frequency acoustic waves, whose excitations we call phonons. So the motivation for this work really starts from this age of information processing, which we're all living through, where we know that the amount of computing that we all use in our laptops and computers and data centers and so on has been increasing very fast for decades, for year after year. And similar has happened with our communication networks, where now fiber optic networks and microwave transmission systems are just all around us, and we continuously use them. And even today, it seems like most of the focus that we have as humanity is going into building on this technology that really starts from transistors. So where people are scaling up chips to have trillions of transistors, which dissipate enormous amounts of power. So people are really trying to push that to the limits, and that's great. But most of our effort is going into these semiconductor technologies. Even communication-wise, it seems to me like most of the communication is actually happening on these transistor chips. not really between different cities, for example. And then also into the associated software that builds on this transistor technology. And even though this is perhaps not really tapering off yet, for example, with the advent of this generative AI technology that many people are now excited about, it seems to me like it's kind of an accident of history that we happen to, if you think about the space of all possible inventions that we could make, sort of the urn of inventions, some people call it, it seems to be kind of like an accident of history that we happen to take out the transistor there first. And then we built our whole world around the transistor, really, to support that technology. And I think that should really make you wonder, like, what else is in there and what else could we discover in that space of possible devices and ways of using those devices. And perhaps if these three inventors here of the transistors had been had a slightly different focus, or perhaps if there had been less of an immediate commercial path with transistor radio towards wide adoption, perhaps we would have gone back into that urn of possible inventions much sooner, and perhaps we would have found things that are better or more interesting in different ways. And that's what now many people are starting to take very seriously again for the last decade or two, where people are starting to take coherence as a starting point for finding things that are very different from the transistor. So if you look at a transistor, it's an amazing device, but the electrons there, they're really colliding with each other, they're interacting with their environment. So they really lose all their coherent properties in its broadest sense. And really, in the end, they end up just encoding a 0 or a 1. And that's then, in the end, all there is to that device in one sense. And even if the limits of these devices were not being tested, with the sizes of these devices shrinking down to the atomic level now, I think it would still be interesting to think about what you could do if you had coherence in a device at a more basic level. And many are now taking that seriously. And that starts even with just taking wave coherence seriously, where wave coherence means that you have a particular frequency or a particular color, and it can interfere with itself in various ways. And there might be essentially dissipation-free ways to compute Fourier transforms or to various computations. And for example, do optical computing with waves is one example of that. But then perhaps an even more fundamental way of exploiting coherence is what people are calling quantum coherence, where instead of using bits that are a 0 or a 1, you try to use these concepts of superposition, where instead of just 0 or 1, you have some kind of counterintuitive combination of 0 or 1 that's really neither. And in addition, when you have multiple quantum bits or qubits, you can spread out the information between them in a way that perhaps lets you use some kind of parallelism so that you can compute certain things perhaps much faster. And this is what led, for example, Richard Feynman to say, nature isn't classical, damn it. And if you want to simulate nature, you really better make sure that your computing device is actually quantum mechanical itself. And I think he also said something like, and it doesn't look so easy, or something like that. And I think that's what we're all experiencing, or many of us are experiencing. Like, it doesn't look so easy to do this, and that's what we as a group want to help with, is to make it easier to do that. So that's where our focus is. And so there's now quite a variety of platforms where people are trying to exploit these superposition entanglement concepts. For example, people are trying to use trapped ions, neutral atoms, but our focus is really mainly on the superconducting microwave technologies as well as optical technologies. And the reason for that is perhaps partly sociological, because I happen to have the opportunity to get trained in these areas, of course, and you can't always choose that. But I think, certainly with benefit of hindsight, these technologies, they're in a sense actually the closest to what's already working in the classical domain. So this is actually, in a sense, quite close to electronic chips, except it uses quantum coherence. And this is, in a sense, quite close to fiber networks and optical data center technologies. And so, and also in both of these cases, so with these publications, for example, people have already used these systems to do some computations with at least much lower energy or much shorter time to do some certain sampling problems that seem very hard, even on the largest classical supercomputers. So I think that's certainly a good place to start. Yeah, and then if we look at state-of-the-art experiments trying to use these superconducting microwave processors, for example, like those built right here at Chalmers or at companies like IBM and Google, these have perhaps order 100 qubits, and they might be able to do 100 or 1,000 operations before there's a mistake somewhere, and then you might have to restart to try again right now. And if you look at these experiments, impressive as they are, so they're extremely impressive with extremely complicated control problems. That I think should really make us think back of the day when classical computers were still in their early days, and that doesn't look so very different to me, except for perhaps there's some cryogenics here. So, and at least in this case, eventually we found a way to make this work and to make this be useful to people. So we don't know if this will be possible, but it looks like there's at least a chance we can make this work. So I think we should try. So the big question that many people are trying to help with is how can we now scale up these devices? So increase the number of qubits, as well as reduce the number of mistakes that you make. So reduce the errors. Some people have made graphs for this, where you plot the errors of the algorithms on the y-axis and the number of qubits on the x-axis. And then there is this path that we're trying to take, where you go to many qubits, perhaps 1 million, and you go to perhaps errors as low as 10 to the minus 4, but even lower would be better, of course. And then in this region, there are at least some known algorithms that we could run on these devices, where if you have such a big system that has such low errors, then these algorithms seem like they should be very interesting. And this is where we are today. So we're trying to get to this regime of fault-tolerant operation. So then if you look at one of these experiments here, this was with order 50 qubits. You see that there's really many cables, and it's as if you're trying to control in the classical domain every transistor with an individual cable, which of course we're not doing right now. In your phone or in your laptop, you have many billions of transistors, and you're not controlling every one of them yourself. Instead, there are all these layers of hierarchy, and there's memory, so you can put information in a memory for a while and then take it back so that you can process it. And that is right now completely missing in the quantum case. So one big challenge is that we not just have to be able to process, but we have to be able to store quantum information as well. And that could be perhaps in the form of phonons or microwaves or spins or various other ways of doing that. Another challenge is that we cannot connect these different small quantum computers to each other very well right now. And so there is this transfer problem. Like, how do we take the information from this small quantum computer and then send it into perhaps a satellite network or a fiber network, and then connect them to each other so that you can do more overall. And so the challenge there really is in these interfaces. How do you connect the processor to a storage unit? How do you connect the processor to a transfer element, and so on? And that brings us to these hybrid quantum devices, where you try to combine microwave technologies with perhaps mechanical or optical technologies. And whether you see this as an application-oriented problem or a fundamental science problem is perhaps a little bit of your personal taste. I think this brings together all these different disciplines, so it's definitely both fundamental and application-oriented to me. So let me start by talking then about the transfer problem. So how do we get information to go over, for example, large distances from these processors? There are quite a few different options. They're not even all here. But the main one that we are interested in as a group is to use optical fiber to connect these small quantum computers to each other. And the reason for that is that optical fiber has these really good, really low losses and really low thermal occupation, even at room temperature. So if you would find a way to get the information there, that seems like a really good idea. But it turns out that that part is just quite difficult. So the question is, how do you take the information from the processor, which is at microwave frequencies, into the fiber, which is at optical frequencies? So then you need some kind of a transducer that does that, because these frequencies are very different from each other. That will be quite difficult then to do. But if you would succeed at that, then there is this vision of building larger and larger synthetic quantum systems where perhaps we can do interesting or simulations of certain chemical reactions or other useful things, perhaps. So that brings me to this topic of microwave optics quantum transduction, where we want to build some kind of a transducer device that takes a microwave photon and converts it into an optical photon, or the other way around. Really, at its most basic level, what you need is some kind of a black box. Like, we don't know yet what's going to be in there, but some kind of box that takes a microwave photon, which is this white arrow here. It annihilates it, and then it makes an optical photon. So you come in with a microwave photon here, it goes through the box, and then you get an optical photon, or the other way around from that direction. And to do that, you need some form of pumping, because the energy difference between these two is just very big. So you need some pump to supply energy to do that. And that is the red arrow there. Okay, so and if this would work, if you would manage to build this, you could take a quantum state. Here, this is the state of a single photon that is in the microwave regime, and then send it through the box, and now it would be in the optical domain. So in essence, really, that's all you're trying to do. It just turns out to be very hard to do that while not actually destroying the state. And so the problem is that you're trying to do a form of frequency conversion while protecting the coherence in that state. And so really this black box, whatever is in there, should not be measuring the state, because we know in quantum mechanics, when you measure, you destroy the coherent properties. So when there's interaction with the environment, you lose the coherence. Yes, and so you need this optical pump, and that will turn out to be the main limitation also associated with these devices, that you need the fact that you need a pump. And so there's two kinds of these transducers. The one that I just described is the frequency shifter, where you shift the frequency from microwave to optical domain, or from optical to microwave domain. There's another mode of operation for these devices, which is called the pair generator mode. And that one also is actually very important, and both you can use to send information between the two domains. And in the pair generator case, instead of the pump being on the left here, you have it on the right of the energy diagram. And now the optical pump is generating a pair. So it's generating an optical photon and a microwave photon here, for example. So you can imagine that case of either you do nothing, or you have a small probability of generating a pair of an optical and a microwave photon in that case. Just for the rest of the presentation, I'll use this symbol T to show that it could be either of these two in that case. Okay, so then we get to how to actually build these transducers, and how to implement this sort of energy diagram that I just showed. So in this energy diagram, you have some form of mixing between at least 3 waves, could be more, but there's at least 3 waves. And there's various ways to implement this 3-wave mixing, and not all are even shown here. But the ones that we're most interested in are the electro-optic and the acousto-optic approach to doing that. And that is partly for reasons that will become clear in the rest of the slides relating to energy dissipation, and partly because these are also technologies that are already out there commercially for these fiber communication networks, for example. So there's already a lot of knowledge into how to building these. So they're perhaps closest to what classical technology can already do. So so I've been working with both, but at Chalmers now at least we're focusing mainly on the acousto-optic, where in the acousto-optic approach you really have a beam of light, and you're sending a microwave signal that makes an acoustic wave, and then the acoustic wave scatters, or like it frequency shifts the light and also changes its direction. So it's kind of like a Doppler effect that's happening. So, and then before I say a little more about how we actually build these acousto-optic devices, I'd like to explain some of the challenges for them, or what the other problems you have to solve if you try to do this. And the main one is, as I alluded to, is related to the pump light. So you need some kind of pump in this mixing process. And that pump is really the source of most of the problems in these devices. First of all, you need the pump to be strong to make the interaction there strong enough so that it actually happens. But also, if you make it too strong, then some of the pump light will be absorbed, and there will be some heating at your device, and that heating leads to noise, and then the device actually doesn't work anymore. So it has to be strong, but not too strong, and those 2 points actually might not overlap with each other. So that's the main problem, is that there's a trade-off between how fast you can communicate, so the transfer rate, and the noise in the system. And so to break that trade-off, what I think we really have to do as a community working on these transducers is focus on reducing how much pump energy you're losing every time you're converting a qubit between these two domains. So this is sort of the dissipated energy per qubit. And in the classical world of data centers, this is already quite well known as where people talk about dissipated energy per bit then. But in the quantum case, for some reason, many people have not really acknowledged that yet, that is the key problem here. So, and to do that, so to reduce the dissipated energy in the system, so to try to break that trade-off between the rate and the noise, there's a simplified figure of merit where this whole problem gets better. The better the optical quality of the structure is, actually goes as the square of that, because you care about it twice. Once because you don't want the light to get absorbed, and once because the better the optical quality is, the less power you need in the first place. And then the other aspect of it is that you need a small volume to make the interaction strong. So really the key figure of merit in the whole thing is perhaps this. Now there are other things, so it's just a simplified figure of merit. So that's the main thing. And then another constraint that we're trying to put on ourselves, and not all groups are doing that, is that we want the devices to be mass manufacturable, so that if we actually succeed at this, we could actually scale it up to be useful and not only an interesting science experiment. And that's how you then end up with this concept of building integrated chip scale devices that try to convert photons between these two domains. And then somewhere in this device, there will be this pump light that gets scattered and absorbed. And then that's what's going to create these problems relating to heating of the device, but also heating of the environment. And that scattered pump light would also be destroying the superconductivity. So there's like many of the problems come from that pump light. And then something that we're focusing on is that if you try to limit the heating in the device, instead of the simplified figure of merit, can be slightly improved by adding, or should be updated to add the area over which there is contact with the substrate. So to say basically how fast can the heat leak away into the substrate. So the heat that you get from this pump light being absorbed. So there's quite a few challenges, and then another one is that you end up with vastly different scales, because the microwave frequencies have sort of centimeter, millimeter wavelengths, while optical frequencies only have like a micron wavelength. So you have very different scales in these devices, which can create problems. And so our approach is this mainly right now this acousto-optic modulator approach, where we in a way try to find like what is the quantum limit of an acousto-optic modulator. So try to, in essence, build an acousto-optic modulator, but that works for single quanta. And then this would look something like this, or sketch-wise, where you have a superconducting circuit, which has could have a qubit, and then that's connected to a piezoelectric element, and then in piezoelectric element, you connect to a mechanical mode, which is for us mainly at gigahertz frequencies, and then that mechanical mode can frequency shift the light in an optical cavity. And so that's where this three-wave mixing happens that we talked about previously. And so then you choose whether you have this or this interaction by changing the frequency of this optical pump. So depending on that frequency, you can choose that. And then you have a bunch of scattering happening there, which is causing all these problems. And so you might have to protect the superconducting circuit with some kind of barrier stopping these optical photons as well. Okay, so in an integrated device, you'd have some piezo region, some of the mechanical region, which then would couple to a fiber there. And these regions, they have different requirements. In one case, you want strong piezo interaction. In the other case, you want strong optomechanical interaction. And so you might also need different materials. So we are most interested, for example, in lithium niobate for piezo and silicon for the mechanical region. And so then you have to find ways to combine these materials as well. And then in an actual device, and this is from former colleagues who led this work, an actual device, this would look like this, where this is the optomechanical region and this is the piezo region. But these devices are, of course, quite hard to build. So this is several years of effort for. Okay, so but then the main reason that we're interested in these acoustic devices is really this dissipated energy. And if you estimate what kind of numbers you could get, perhaps we're not even that far from these numbers. You might dissipate on the order of 100 femtojoules of pump energy for every qubit that you convert. And if you then calculate, how much power could I dissipate in these cryo systems, that might be 10 microwatts roughly. So then in principle, you could be sending one day 100 million qubits per second if you simply divide these numbers by each other. And that's, no one is even close to that. People are trying to do this for a single qubit, but it shows perhaps where we could go in the future. So let me say something about the state of the art. So in terms of efficiencies, so they've been going up quite fast. So the efficiency, I mean, how many optical photons do you get per microwave photon? And you want that number to be, 1 ideally. So commercial devices that you can just buy, they're perhaps, if you were to try to use that for something quantum, you might have to try 10 billion times with a microwave photon before you get an optical photon. And then people have been improving over that basically every year since people got interested in that in the academic community. And so in these piezo mechanical devices that we're interested in, it's been going up by kind of like an order of magnitude every year for 6 years or 7 years or something like that. And that doesn't mean that it will keep going up, of course. Like we don't know, like it has to saturate at some point. You cannot go higher than 100%, and we don't know exactly where it's going to saturate. But at least that looks kind of promising in terms of, because it's quite a small field actually. There's only 5 or 10 groups trying that. But the problem is that while this is exciting, I would say, like the efficiencies that you actually need and the noise that you need to do direct transfer, they're quite demanding. So you need to get really close here to 1 to do useful state transfer. So and especially with high fidelity then. Many in the field believe that perhaps it's better to first look at not this approach of directly converting the quantum information, so just frequency shifting, but instead looking at the approach where you do this pair generation interaction, and that interaction then would be not deterministic; it would be probabilistic, but it would be with very high fidelity if it works. And so an experiment that quite a few groups are interested in, and no one has done yet, is this potential experiment where you'd have a qubit in one dilution refrigerator and a qubit in another dilution refrigerator, and then you have transducers, and then you split, so you do this pair generation. So sometimes you generate a microwave and an optical photon, and then when that happens, the optical photon goes into this path here, and then it goes to a beam splitter, and then you get a click on one of these detectors. And then when you get that click, you don't know whether the photon came from here or from here. And then that way you end up generating an entangled state. And then once you have that entangled state, you can use that to transfer the quantum information from this fridge to that fridge, for example. And so no one's done that yet, and that's a goal that many in the field share. And the elements you need for this are wish path erasure. So you need to make sure that you don't know where the photon's coming from. You need a beam splitter, like here. You need filters here to get rid of this pump light, and you need very good photon detectors, like here. And this is actually quite similar to what people in the optical quantum processing community are actually doing also already. And that will come back later. As you might have noticed on the efficiency plot, there are actually devices that have better efficiencies than what these gigahertz mechanical systems have. And so let me say a word on why we are interested in the gigahertz case especially. And that is because if in principle these devices they promise high rates of communication, and that comes back to this energy per qubit. So if you plot on one axis the losses, the optical losses, and on another axis the interaction rate for this free-wave mixing, then you can plot lines for how fast you can communicate, and then it looks like at least the limit for the piezo optomechanical systems could be as high as 100 megahertz, and so that's why these look interesting. So that's where the gigahertz mechanics is. And that the reason for that is really that gigahertz mechanics has a similar wavelength as an optical photon. So they both have wavelengths around the microns, so they can interact with each other very well. But the problem is that right now, or it's actually not possible to get these numbers, because these numbers are limited by how much power you can dissipate in one of these cryogenic systems. And actually, you cannot dissipate even close to this amount of power, because when you even dissipate just a nanowatt instead of 10 microwatts, then you're already limited by the heating in the device instead of the heating in the dilution fridge. So that is what actually is limiting all these devices now, and that's why we have to lower these dissipated energies. So in principle, people could, or in theory, we might get transfer rates that are megahertz, but in practice, all the devices are limited to perhaps 10 or 100 kilohertz of generation rates. And so that's the problem that we're interested in, and that's certainly not the low-hanging fruit, but perhaps the most important problem to really make this useful. And so that's what we're trying to do, is we're trying to get around that trade-off by using thermal anchoring and by lowering the dissipated energy. And so that brings us to the first experimental result from our lab, which is focusing on improving this thermal anchoring. So trying to let the heat escape faster than it does in existing devices. So in existing devices, most groups use suspended structures. So there is like a small silicon region where the optomechanical interaction is happening. And in that region, some of the pump is being absorbed, and then you get some heating, but the heat actually can't leak away, at least in this cross-section. Then if you look in the other cross-section along the structure, which is sort of like a one-dimensional optomechanical crystal structure, the heat has to leak away via these very tiny bridges there. So it's very, very slow, this heat leakage. And so that's why, for example, the Painter group at Caltech started developing these two-dimensional optomechanical crystals. So this is like an optomechanical component where it's not just a one-dimensional beam, it's actually connected over a whole slab, so also on the sides of the beam. So now the heat can leak away to the sides as well, but still through very narrow silicon bridges. So it still seems like this is very far from what you could actually achieve if you were to be able to clamp the structures or to anchor them better. And so that brings us to this question of how can we let the heat phonons, so the incoherent heat phonons, leak away fast, while letting the coherent phonons, which we need, stay there for quite long. And so this really seems not easy, but there might be some ways to do this. And so we got started then thinking about this question. Perhaps we can actually fully attach this optomechanical region to its substrate. And if you could do that, we'd certainly, or would expect this thermal anchoring to be better. We'd also expect the design to be more robust because you don't need to trap the phonons in plane as much anymore. But perhaps the downside could be that the mechanical quality factor could be lower. But then again, that is not as important. It's not in the main figure of merit for these devices. Yes, so let me then move to how we're doing that. So the question is, how do you keep the coherent phonons there while letting the incoherent phonons leak out? And so there's of course a reason that many people have been using these suspended devices, and that is that it's easier to keep the phonons you care about there. But if you do it to the way that people do it in these suspended devices, there you have two optical waves that go in the same direction typically. So you have a co-propagating interaction, and then you end up with a mechanical wave vector that's very low, and this could basically just leak into any surface acoustic wave or bulk acoustic wave on the chip. So then we got started thinking about instead using a counter-propagating configuration where the optical pump and the sideband are going in a different direction. And when you do that, because of conservation of momentum, you end up with mechanical wave vectors that are very long. And then they could actually be so long that they cannot talk to anything in the substrate. So you could still confine the mechanical modes there. So that's what we then focused on and started focusing on. And then if you'd succeed at that, would hopefully find some operating point where you are very far from any of the states in the substrate of the chip. And so that's at least the principle behind it. But then perhaps the hardest part is actually to find modes that realize this. So to find modes that an optical mode and a mechanical mode that can talk to each other efficiently. And so that perhaps about a year or two later, we actually found these modes. And so this step was very difficult. And so we found this optical mode and this mechanical mode. So Johan and Paul mainly led this work. And and it turned out that when we simulated this, it looked like this could really be almost as good as suspended devices in terms of interaction rate, which we were very happy with, even just on paper. And then we made these devices, and just in a nutshell, it seemed like they worked really well at room temperature, but we don't know yet if they work really well at low temperatures also. So that's still under investigation for us. Okay, so these devices are actually quite close to the suspended ones, at least at room temperature. There's some room there for improvement, but it doesn't need to be that much better. Let me just check the time. Okay, so this brings me to so there's now this challenge of that we have to build an entire transducer, and this is a big challenge that our whole group is involved with, and that's all I say about it for now. So this brings me to part two of the why we're working on microwave optics transduction. And if you take sort of a step back and you look at the bigger picture of why we're doing these things, really it's about combining the strengths of coherent microwaves and optics. So microwaves has this really good quantum nonlinearity where you can do nonlinear operations very well. Then optics has this large range, and then their weaknesses are also complementary. So that's why these could fit together so well. And then the phonons, they come in because they're a very good interface, at least in principle. So, but then if you take this step back and you ask like, what are actually the different strengths of these systems? You start noticing different possible applications for combining these elements. And one is in the classical domain, which I'll just skip for now, but there's a range of applications there which usually involve power restrictions of some kind or large amounts of data. But then another one is back in the quantum domain, where instead of seeing the optics as adding range to the microwave system, so making networks, you could also flip the very same thing around, and you could say, yeah, but actually what we're doing is we're adding nonlinearity to the optical systems, because the microwave systems, they're so good in terms of processing and doing operations. So really, how could we benefit from that? And that's not really the same question as what people have been asking so far. So perhaps there's some kind of optimum that involves some combination of the optical quantum processors and the microwave quantum processors. And so I'll have to be brief on this, but these optical quantum processors, what they really would like to have is some kind of nonlinearity, so some kind of small quantum state that has a little bit of entanglement in it. For example, they would be very happy with a state like this, where you have some entanglement already, and then once they have that state, they could make bigger and bigger entangled states very fast. But to make the states, they need some amount of nonlinearity because they need to implement some gates. So and then that's what they don't have. So they instead right now these approaches in the conventional path, they're trying to generate these kinds of states with all optical pair generation in a process that's a lot like the one that happens in our transducer in the pair generation state case. But these processes, they're really probabilistic. And so it's very hard to start from the small amounts of nonlinearity that they have and then amplify it to the much bigger nonlinearity that they need. So the overhead for that is really large. They need to do a lot of multiplexing to do that. So basically waiting until it happens and then making very big circuits until you're sure that it happens somewhere. So then instead, we got thinking about, can't we use the superconducting microwave circuit as a resource state generator for these optical systems? And if you'd have a perfect transducer, perhaps we'd already been doing that. But then the question remains how to do this with imperfect transducers, or at least that's one of the questions there. And so I won't be able to get into the details, but then along with Trond and Anton, we came up with this scheme where you could use an imperfect transducer to make an optical resource state. And so this combines a microwave processor and an optical dual rail processor where you have a photon here or here, essentially. And so the scheme, really briefly, the scheme starts from this pair generation we already talked about. Then there's a swap from a phonon to a microwave photon. And then there's a parity check, which then heralds the creation of a microwave optical bell pair. So where the entanglement is sort of partly in the optical and partly in the microwave domain. And then once you have that, you can start doing operations in the microwave domain. So controlled Z gates, creating superpositions. And then you can make essentially any optical resource state you want using the microwave nonlinearity and an imperfect transducer. So, for more about that, I think I'm allowed to invite you to the QT Monthly discussion on Monday at 1, where Trond will be able to explain this in much better than I can right now. But it looks at least like, depending on how fast transducers are improving, it looks like this could actually work quite well. But the takeaway, or at least sort of in an intuitive sense, the takeaway I think is like we should perhaps not just think about adding range to microwaves, but also about adding nonlinearity to optics. And perhaps really we'll end up with some kind of merger, because in the end, how different are these approaches still from each other? And perhaps in the end, you end up rearranging how you would build this large quantum system in a data center. Instead of connecting quantum processors to each other like this, you might arrange them like this, where each microwave processor is feeding resource states into an optical system. And this optical system is actually really, really good at doing fast linear operations to get the answer out of the algorithm you want to run. So the building blocks for this are really quite similar to those building blocks that you need for the more conventional approach. So you still need superconducting processors, transducers. You need to have Witch path erasure and optical photon detector. So perhaps the question is just how much time do we want the quantum information to spend in optics versus in microwaves? And perhaps there will be some middle ground there. Okay, and I just want to say a brief word about storage, where we haven't really done much yet at Chalmers, but we're interested in this topic. And so on storage, the background is that in my previous group, my colleagues led an experiment where they measured the energy levels of this nanomechanical oscillator, so they could see, oh, I have like 1 phonon, 2 phonons, 3 phonons, and so on, in a non-demolition way. So like actually reading out how many photons you have, like you would do in the microwave domain. And then around the same time, the painter group at Caltech found a very similar structure in silicon. So this is in lithium niobate for the piezoelectric interaction, found in silicon where they see lifetime order of seconds, which really could be very useful for this storage aspects. And so this is that experiment there, which is like far above other mechanical systems. And so now this experiment was optically read out, and to use it in superconducting circuits, you need to make this electrically read out, and that's really not obvious at all how to do that. But if you could do that, you'd have this device with a very high Q. It could be very compact because of the mechanical wavelength only being a micron, and essentially no crosstalk because you can make phononic band gaps that completely stop these systems talking to each other, even when they're just microns away. But this is more of a goal, and really perhaps right now no one knows how to do this, but we're interested in that. Okay, and so coming back to how I started, we're trying to make these state conversion interfaces, and this is a hard problem, but I think one we'll be happy to work on for a long time. And there's also a longer story to be told another day about all the strengths and weaknesses of microwaves and optics and acoustics, but perhaps that's for in the coffee break. Yeah, and then with this, I would like to thank everyone. So I would like to acknowledge the group without whom this is not possible. I would also like to acknowledge my former group, where I learned a lot from different people. And I'm especially thankful to my former advisor, Amir Safag-Naimi, without whom I wouldn't know much about transducers, probably. And also, I had this period in my PhD in Ghent, where I got immense freedom and learned from these people. So Roel Baats, for example. And we're also, of course, happy to get the support from WACT. Without that support, there would have been no lab, and probably no people either. So and also all the other funding agencies that have supported our group and also me over all these years. Yeah, and then finally, I want to acknowledge my wife, Emma, who has enabled this work really in countless ways, and also our little kids here, who are reminding me continuously that time is a bit too precious to do anything but the important things or be with people you like, even if those things might actually fail. Yeah, and then with this, I'd like to leave you with the thought of this urn of inventions and what else might be in that urn. And perhaps I would hope that the inventors of the transistor, even if they think this will probably fail, they at least give us some kind of nod of approval for trying. So thank you.
Thank you very much, Rafael. Very interesting talk. Any questions? Yes.
Yeah, thanks for a very inspiring talk. You mentioned the use of superconductors as to provide resource states to the optics. And you had examples of single photons. And superconductors were very good at creating larger non-classical states. How do you see them to be useful?
Yeah, so it's especially for those larger states that we're really interested in, and that's what that scheme would do. So, but I couldn't get into the details. So, and Tron will be able to do that better on Monday. But let me go back. So here, for example, when a transducer is operated in this sort of pair generation regime, you can use that to make, for example, this resource state, which is a 6-ring, where there's entanglement between each of these qubits, and each of the gray circles here is really partly in the optical and partly in the microwave domain. And then so you're doing the nonlinear operations in the microwave domain to make the entanglement. And then you can do a Hadamard gate in the microwave domain. This is what Chalmers found out. And then you can measure out the microwave qubits, and you end up with a purely optical research state. So this is about making larger research states as well. It's really not just about the single photon case. So it actually might get more interesting the larger the state, because you need more and more nonlinearity an entanglement to make it.
Is this multiple nodes that are entangling, or it's a single node in which you're exploiting?
Each qubit is a dual rail. Sorry, so each qubit is a dual rail system like this, where you have two rails, where you can have a photon here or here, for example. So yes, so it's multiple. There's more than one node.
But what about cat states, GKP, or?
Yes, so yeah, so we initially also talked a little bit about GKP, and then there's actually some previous work about that as well, where you could make a GKP in the microwave domain and then teleport it to optics, for example. So, yeah. So that is possible, I think, in principle.
Thanks.
Oh, great talk. I have a question regarding how good your transducer needs to be useful, and also, I mean, you show these if you extend the range of the sort of microwave domain, or you extend the nonlinear of the optical. Are these thresholds for being useful different whether you go one way or the other?
Yeah, well, that's a good question, and we're thinking about that question right now, I would say. So I don't have a full answer. It seems to me like perhaps it's a little bit easier to entangle two microwave circuits than to get the entanglement towards the optics, but that depends a lot on what sort of devices you're thinking about. For example, if we go back to the scheme where you try to entangle. So in this scheme, if there was some imperfection here from the transducer getting into a fiber, that would be reducing the rate of the experiment, but not the fidelity necessarily. And that would not be the same in the case of using these resource states. But there you would actually care about that efficiency more. So depending on how good those interfaces can be from a chip to a fiber, for example, we have a different answer. So it's not full.
Yeah, but could you so now people can do a few percent conversion, even maybe up to 50%.
Yes. So
is that good enough? Of course, you want to as good as possible, but how far would you really make an effort to go before you can do something really useful?
Yes, so I think right now with systems that we already have, with these systems, for example, we could be trying to do this sort of entanglement between microwave circuits for sure. Yeah, I think that would work. The rate would just be quite low. And then it would be a very interesting science experiment, but perhaps less interesting for scaling right now. So yes, I think there is no barrier to trying that right now.
Okay, thanks for the wonderful talk. I wanted to ask concerning this plot. This is one metric, right? Efficiency. The other metric is noise. Can you comment a bit on added noise in your approach compared to other approaches, or is it not a limit at all?
Yeah.
Also,
yeah. So we haven't built full transducers here yet, right? But the way we're trying to do that is really focused on if I go back. It's really focused on trying to improve the trade-off between these two, because there is this trade-off between how fast you can do the experiment, so how often you can do a communication between microwaves and optics, and then the noise involved in that process. So really there's a trade-off between the rate of the experiment and the noise in the experiment. And to improve that trade-off, we're really focused then on reducing the energy that's dissipated. So that means improving optical quality, and also on improving the thermal anchoring. So this is all focused on noise, but we don't know yet how good the noise is going to be in this approach where it's non-suspended. So that we'll just have to measure, I fear.
Yeah, thanks for the talk. I was wondering about you talked about having this counter-propagating pump, right? And like, how weak is that interaction, or like, do they interact?
Yes. So that's definitely something we were concerned about when we were thinking about this idea first, is that it could be a lot harder to get strong interactions in this case, because the profile of the optics is more complicated. So you have two counter-propagating optical waves where the phases are sort of changing. So it could seem like it could be harder than in the co-propagating case to get a strong interaction. But then it turned out that after a lot of searching and trial and error, we could actually find designs where the interaction is half a megahertz, and this is measured now. And in the suspended systems, it's around the megahertz in the best ones. So it's not so far off. And we think there's still some potential for growth there also.
Okay. Any other questions? Okay, catch up.
Thanks for the presentation, Raphael. I maybe want to ask about the future perspective, but if we send the signal through the optical fiber, even it's a very nice fiber, the signal will attenuate some distance. We'll want to amplify that. Will it destroy the quantum state? And what is the solution?
Yes, so if you were to simply send a photon in a fiber, eventually the information will get lost, roughly perhaps tens of kilometers or something like that. And that is why people are thinking of building what is called quantum repeaters. So instead of a regular amplifier where you try to amplify the signal, we'll build some kind of quantum amplifier that amplifies the signal without adding noise. Because if you normally amplify, you would be adding noise to the system. And for these quantum repeaters, we also think that these transducers could be useful, actually, because to build the quantum repeaters, you need to do some processing, and that processing could be good in the microwave domain, but the photon could be good in the optical domain. So then you might need some conversion there as well.
Thank you.
Okay. Thank you. Any last questions? If not, let me congratulate you to being a docent or the relationship professor of the whole token from the department. And we have, of course, the diploma for docent. Let me be the first to congratulate you.
Thank you.
With that, I think there might be some refreshments outside. So let's go and go those. Thank you.